Hi, in this video, we're going to take a look at the pairwise relative semivariogram. All right, well, what is a pairwise relative semivariogram? That's an excellent question. Thank you for asking. All right, so this is a visualization for us to be able to detect spatial dependence. Now, you might respond, well, whoa, don't we have the variogram for that? When I'm doing spatial statistics, you've gone on and on and on about the variogram. Why are we talking about the pairwise relative variogram now? Well, it's going to work out that this is a better approach when our data is skewed or spatially clustered. Okay, so let's dig into it. All right, so this is modified from a vignette coming from the gstat package. Ed Zur is the author. All right, the pairwise relative semivariogram is a geostatistical tool implemented in the R package gstat. It provides a more effective way to reveal spatial correlation structures in skewed or clustered data compared to traditional variogram. All right, and now that I'm looking at it, maybe it'd be better to say spatial dependence, but we'll just keep it rolling. All right, so we want to use the spatial relative variogram instead of a regular variogram for detecting spatial autocorrelation when our data is skewed or it's clustered. All right, so now here is the formula for it. Okay, so if Z is the variable that I'm interested in, so that's like what we actually observed in our counts, S is the location that we're measuring our data at, because remember, we're doing spatial statistics. S is a location, S plus H is another location, then Z is the numeric value of what we're measuring. All right, and you'll notice that here I'm taking the difference in the numerator and the sum in the denominator, multiplying by 2, and then I'm squaring. Now, we could definitely have like simplified this because we got a bunch of 2's floating around, but this is what I'm copy and pasting. So I'm going to keep, to be consistent, going to keep it this way. And then, we, take an average overall. All right. So now, when we have actual data on the ground, we're not going to have an exact H. We're going to do like a range of distance values and when we do the calculations. So this is claimed to reveal spatial structure correlation better when data is skewed or it's clustered. Okay, so we're going to take a cluster data set that is in the package. And also, there is GSLIB analysis of this also. And towards the end, we'll take a quick look at that. I'm not going to really dwell on it too much. All right, so GStat provides a computation of the pairwise relative semivariogram as long as you're dealing with version 1.02 or later. Basically, anytime you load it, you're going to get it at this point. The following code provides an example and verification of the computation using DirectR code. And then later, towards the bottom, we'll take a look at the output of GSLIB. All right, so we're going to import our data set in. And then, we're going to start working with it. And, now, one thing we're going to need to do, we'll need to convert our data to a spatial points data frame in the SP package. Okay, so let's look at some code. All right, here I'm just setting up my workspace. So I'm making sure I don't have any artifacts floating around, making sure that I don't get blasted in the face with a ton of digits. I prefer scientific notation. I always like piping and ggplots. I set up my working directory and like that. All right, so now let's go ahead and read in our data. And so this is in the gstat package, and we read in from a text file, and the header is true. So let's go ahead and take a look at it. And so we can see that we've got our X and our Y, which are our coordinates. We have our primary, our secondary, and our decluttering weights. So the primary is going to be the one that we're going to focus on the most. All right, so remember, we're doing spatial statistics, so I definitely need to have some coordinates going on. So I'm going to go ahead and use SP's coordinate function to assign X and Y as the coordinates. And let's go ahead and visualize the primary right out of the gate. That's one we're interested in. So notice two things about this. First and foremost, notice that we have clustering. We've got the X's going on of the actual data points that we're looking at. Next thing that we have is how many light colored dots are there? There aren't very many. Look at the scale of the primary value, and you can see that it goes above 50 on the scale, but to my eyes, I only see one of them. So what's set up here is that we have skewed data. This is skewed right and is clustered. And so the hypothesis of this vignette is that we don't want to use the regular variogram. We want to use the pairwise relative semivariogram instead. All right, we can also do this for the secondary. And so you notice we have the same locations, but things are not as skewed as they were previously. And then we can also do this with the weights, but that's not really that important to us here. All right, so we're going to specify a sequence of lag boundaries that corresponds to the other analysis that was performed and compute a regular variogram using these boundaries. All right, so you can see that I'm going to start at really at 2.5, and then I'm going to add 5 every single time until I get above the maximum observed value. And then let's go ahead and do the gstat variogram. Here, I'm not pulling in any covariates. And so now, these boundaries, indicates, the cutoffs for what's going to happen. And so we can also do a relative pairwise variogram. And here, very nice. All I have to do is put pairwise relative equal to true. Boom, I've got 2 variograms going on. And so let's go ahead and take a look. Remember that variograms are saved in a data frame format. And let's plot them and take a look at these side by side. Okay, so left-hand side, the variogram should look like an increasing function that, follow my mouse cursor. It should kind of look like from a starting point at the axis at 0, it goes up and then it flattens out. Okay, and that's what we should see with this, with practically any situation we're talking about. But what do I see instead? I actually see a decreasing slope off of my dots, and I see that the variance is like decreasing as we get farther apart. That goes against my intuition on this. My intuition is that points that are closer together are going to have less variability between them than 2 points that are farther apart. Okay, so this plot is indicating that points that are closer together have more variability relative to each other than 2 points that are far apart. Now, that doesn't make sense. Okay, so what we're going to do, let's use instead a pairwise relative semivariogram. And you'll notice that, at this point, we got started, and, it's coming up, and then it flattens out. Okay. Now this looks reasonable to my eyes as I look through this. Okay. It's not exactly what I was expecting. I thought I would adhere a little bit better tightly. When we get farther out, don't be surprised if we get a little bit of wiggle going on the right-hand side. That's okay. So the regular variogram on the left and the pairwise relative variogram on the cluster data set. Okay, so let's go ahead and verify with plain R code. The following R code produces the relative pairwise semivariogram for 3 lags. So 0 to 2.5, 2.5 to 7.5, 7.5 to 12. And let's go ahead and run through the computations. I'm going to be doing outer product with a difference. I'm going to do outer product with a summation. And then I'm going to be able to use the ratio of those to very quickly and easily get the computations that I want. So remember, as I go through, I want all the possible pairs considered when I do the computation. And now, when we do our variogram, remember it's a distance that goes along the horizontal axis. And here I've got the distance being computed here. Okay, and so I'm converting it over to a vector, and then I go through and do the computation of the variogram values. So this is the vertical axis of the points. And so here I'm limiting it to between 0 and 2.5 for the distance. Here I'm going from 2.5 to 7.5, and here I'm going from 7.5 to 12.5. And here we can see that by these measurements, the variance between 2 points for the variable of interest, the variability between points increases as they're farther apart. This fits my intuition. This makes sense to me. All right, so let's go ahead and take a look at this in another way. What I'm going to do is I'm going to take the distance. I'm going to take the pairwise variability of it, and then I'm going to plot it as a scatter plot, and then I'm going to do a lowest curve. Okay, so let's go ahead and put that down. All right, so horizontal axis is the distance between the 2 points. The vertical distance is the pairwise relative, the add-in that's in the formula. So this is the difference between the two divided by the sum of the two, like that. And you can see that when I do the smoothing curve, this looks a lot like what a variogram should look like. And now, with data, of course, I do a lowest curve and I go farther out, where I get less data. I get some wiggling going on, but I'm pretty sure that my range should cut off somewhere around, like, let's just go ahead and say 15, because that's an easy number. Here I can see with the nuggets real nicely, go out to 15, and then it levels off. So this looks like what it should look like, and this looks a lot like the pairwise relative variogram that we saw a moment ago. But this visualization was computed in a different manner. Here I use the lowest curve instead of binning and taking the average overall. All right, now the author goes through and compares to the GSLIB output. If you go to the gstat package, you can find this. I went ahead and copied and pasted this. For my purpose, I really don't worry about it too much. Basically things jive overall pretty well, not perfectly. That's typical of when we repeat something with two different softwares. you know, uh, really the punchline of this entire video can be summed up in what I said at the beginning, in that whenever I have skewed and or cluster data, I should use a pairwise relative semivariogram instead of the regular semivariogram. All right. I hope you've enjoyed this video. Life is short. Do math.